moving forward, we want to take the configurations we've learned about and apply them to figuring out valence electrons.
So we've said we care about electrons, where they are in atoms, because they mediate how atoms interact with each other. But if two atoms are going to interact with each other, what really matters is the electrons that are most on the outside of the it's most on the outside of the atom. Okay, and so these are what are going to participate in actual chemical bonding. So the core electrons are then going to be any electrons that are inside that valence kind of level, the electrons that are furthest out. So we've got some depictions here: boron, silicon, and antimony, 3 atoms. We can see that as they grow, boron has 5 total electrons, 3 valence. Silicon has 14 total electrons, 4 valence. And antimony has 51 total electrons, but only 5 valence. It's one of the important things about this that we're going to start to see is that number of valence electrons isn't going to get very high, and that's really important in terms of consistencies among how atoms interact with each other. So when we want to look at electron configuration and figure out what the valence is, when we're looking at the main group of the periodic table, so the parts that go the highest up, the valence is just going to be the highest shell. Okay, so if we look at something like germanium, for example, there's a lot of electrons there, but the electrons that are furthest out have the biggest orbitals, and that corresponds to the highest shell. So in this case, n equals 4 is going to be the highest shell. All right. There's 2 in, we can see the 4s, and 2 in the 4p. So that gives me a total of 4 valence electrons. That also means the 4s and 4p subshells are what make up the valence of germanium. So those are the furthest out subshells. So they are out the further, are what actually mediates, right? It's not necessarily, these are arranged in energy. So we can see that 3D is there, but that full 3D subshell is actually not in the valence. That's because it's lower, right? It's a lower shell, which means it's literally closer to the nucleus. We do have some complications when we hit the transition metals. Now you have higher energy subshells and an unfilled D subshell. So those are both going to be in the valence. So for cobalt, there is a 3D subshell that is unfilled, right? It could go up to 10, it only has 7. And you have the n equals 4 is the highest shell. So what that tells me is I have a total of 9 valence electrons. That would be the 2 plus the 7 that we have right there. And that is going to be the entirety of my valence for cobalt. And it is, again, the 4s, and 3D subshells that make up the valence of cobalt. So let's take a look at some examples here. For each of the following atoms, we want to determine the number of valence electrons and what sublevels make up the valence of these atoms. So I have beryllium, oxygen, sulfur, and chromium. You will note this is not a random selection. These are the same ones we looked at in the last example. So if we want to figure out valence electrons for electron configuration, we want to start by figuring out what the electron configuration of the atom is. I have an electron. Once I have that, I can analyze that to figure out what the valence electrons are. I'm really going to start off, is it the main group or is it a transition metal? Is it one of those metals in the middle? If it's a main group, we just take whatever the highest N is, whatever the highest shell. If it's transition metal, we need to include those unfilled Ds and the highest N. So these 4, again, were not random. These were the 4 that we got the electron configuration of previously. So beryllium, oxygen, sulfur, and chromium, we have those, 1s2, 2s2 for beryllium, oxygen, so on. So beryllium, and when we're looking, that characterization, when we're looking at things being transition metals or not, one of the things that is always going to be characteristic of transition metals is D-type subshells will be the highest. So beryllium, oxygen, sulfur, none of them are in the transition metals. We can see that none of them have a D as that outermost subshell. So for beryllium, the outermost subshell is S, 2s2. So we know that N equals 2 is the highest level. And so then the question is, how many electrons are in N equals 2? Well, in N equals 2, we only have the 2s subshell. We can see that we only have the 1 subshell. However many electrons are in there at 2, there are 2 valence electrons. And so 2s is the subshell that makes up the valence. For oxygen, again, n equals 2 is the highest level. But this time there are two subshells there. I have 2s and 2p that are both in there. So I need to add those two exponents together, the 2 and the 4, to give me 6 total valence electrons. So when we go down to sulfur now on S, again, I want to look at what the highest shell is. I can see in this case that's going to be n equals 3. So I have the 3s2 and the 3p4 that are making it up. Right? Those are the subshells that are in the valence of these atoms. And we can see then that, again, we add the 2 and the 4, and sulfur, again, it's bigger, but it also has 6 valence electrons, just like oxygen. Chromium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. There's a lot of electrons and a lot of different things. But again, we're focusing just on the end, that highest level. Chromium is a transition metal. It shows up in the middle of the periodic table. And so n equals 4 is the highest shell, but there's also a 3d that's unfilled. We can tell it's unfilled because we know that 4 is less than 10, right? A d can have a total of 10 electrons in there, but we haven't hit that. So it's open, it's unfilled. And so because it's unfilled, it can participate in some chemistry. You could put more electrons in there, or take some out. You could do kind of changes. That's why it's part of the valence. So collectively, it's 4s and 3d, and we add those exponents together. 2 plus 4, hey, again, 6 valence electrons. We can see, even though chromium has a much higher total of electrons, has 24 total electrons, it still only has 6 of those that are valence. Because of this Aufbau, this building up, you kind of only have a handful of electrons, or a smaller number of electrons that are actually on the outside of the atom.
One more video to go. Will there be one more question for participation 3026? Who knows?